Okay, hello everybody. I hope we have a little more luck today than yesterday. Yesterday I was streaming from the IBM Zurich Research Lab and we had a network issue, so the stream actually was unusable. So today I'm here in the Basel Swiss Innovation Park. It's here a co-working space in the Allschwil branch, and let's see if it works better. So I will check in the chats if there's someone asking questions, and then I try to answer those questions just online. And let's actually start with a poster. So this is the poster session, the online poster session for the AGU24 conference, currently taking place in Washington, D.C. And we will talk about a TensorLakeHouse, a high-performance open source platform for accelerated geospatial data management with hierarchical statistical indices. That's quite a mouthful, but actually it's a data lakehouse for scientific data. So the idea about this is to organize your data in tensors, so ND arrays, in other words. And the key thing is you are not bound by storage because we work with virtual hypercubes. That means you define the structure of your hypercube, the dimensions, and the data types, and you access a cell, and if the cell is not yet onboarded, then you can specify what should happen. And that's a very, very powerful thing because you can easily work with sparse data and also just compute stuff when it needs to be computed. And the whole thing acts as an intelligent cache. Okay, no questions so far. Then I will continue. So the idea is we have a storage backend. And the storage backend is either a cloud object store like S3 or a normal cluster store like cluster FS or GPFS. We can support key value stores, HBase, HDFS, whatever. So anything you can store data on, basically we can support. So there are two important things. One is how do we get data in and how do we get data out. So let's start with how we do get data in. And for that, let's switch from this poster, since we are here in an online session, to a slide deck. And what we use for data ingest is a library called Claimed. So all our data ingestion code is written in R or shell scripts or in Python, in normal files or in notebooks. And then what the claimed library does for us, it creates a reusable component out of this. So it can create just a zip folder with the code plus all the dependencies. It can create a container image for using Docker or Podman. It can then also automatically generate Kubernetes job YAMLs, Kubeflow component YAMLs, CWL, that stands for Common Workflow Language definitions. Everything you create is available via a CLI, so you can just say claimed space component ID space parameters. And also, since containerless components are supported, it also would run on the traditional HPC workflow managers like LSF, Slurm, PBS, and so on. The way how this works is, so the blue stuff is created by a data scientist, a researcher, or whoever creates the ingest or data processing or transformation pipelines. And then all what's green here is created by the compiler. So you see here, a Docker file is automatically generated. We extract the parameters from the file, so we detect what information goes in and out of those files, and that's then easy to concatenate workflows out of it. Another important thing is parallelization. So all our ingest workflows, they by the way, the whole thing is open source. No, TensorLakeHouse ingest and discovery is open source, and it's using open standards. I didn't mention that at the beginning. Let me just pause for a second to double check if the stream is okay and if there are any questions. No questions. Very good. Okay. Um, okay, let's continue. So the only thing you need to do to write parallel code is to implement one function, which is called grid process. You can also change the name, but by default, we expect to be a function present called grid process. And the signature of the function is basically anything you like, but it could be, for example, a task ID, which then is either a URL where you need to download a file, or a file path where you need to process something, or more complex task description where you have a JSON or a dictionary and everything you need to know to execute a task is given to you in that grid process function. And now you can start as many containers or parallel processes implementing that grid process function. And what we do, we auto-generate coordinator code around this function, which talks to different coordinator backends. So the coordinator code is running in your component locally in your container image on your laptop, wherever your code runs. And then the coordination data store is either a cost bucket, so S3, for example, or a path on a cluster, a shared cluster file system, or a shared database. We discovered that the database suits best, especially for, let's say, post analytics. So if you want to find out how many jobs have been failing and why and so on, it's much faster if you work on SQL database like Postgres than on files and folders, but it's also possible. What the coordinator code which we inject into the component does is it finds out the tasks from a list of files or folders, or from a task list CSV, or from a database table, and then each task then gets logged while it's in process. And if it's processed, it gets marked as processed so that the second worker won't grab it again. And the third thing is, if in case it fails, it's also marked as failed, so we can do recovery. Also, if a worker dies, we remove the dead locked files that it gets processed again by a later worker. So all that stuff, all that thinking is already done and can be used out of the box. So the only thing you need to do is write a function which does a single task, and then call the compiler, and then start as many workers as you like, and you have parallel code. No? That's pretty cool. Let's see. Okay, that's mostly the stuff about ingest. So let's have a look about discovery. So how to get data out. Data out. So we used as a boilerplate the tensor, or let's say the data lakehouse pattern, which gives you a SQL interface. And then you have some query engine like Spark SQL, Presto, Impala, and so on. And then the more modern ones, which actually makes a data lake house, is the capabilities of supporting standard database operations, like, for example, reading data while you ingest data, and you get always consistent results and so on. So those for those reasons, you have Iceberg, Hoodie, or Delta Lake, and usually that stuff runs on top of S3. And what we did is we adopted this pattern, but just replaced a couple of components with other open source, open standard components. And those are, for example, for file storage is Cloud Optimized GeoTIFF and SAR, what we are supporting. For the execution, we use Dask. We tried Ray, but we found out Dask is more stable and better suited, especially since it's very tightly integrated into that Xarray and SAR ecosystem. And yeah, I'm already mentioning it. Xarray is our low-level query API. So what we do is we create lazy Xarrays that they are backed by a Dask cluster, and then on top of Xarray, so you can either use directly Xarray, or you can use OpenEO, which is also an open standard, which gives you a more coarse grainer access to different operations that wraps the Xarray. And one key thing of OpenEO is also that it is based on an execution graph. It's also true that in the case where you use Xarray and Dask, you will also get the Dask graph. But in the case of an OpenEO graph, this is something you can easily serialize, and you can cut it. And what we do with it is then we do federated queries. So we cut the graph at certain positions and then send subgraphs to different data centers, which all offer the OpenIO API on the Tensor Lakehouse installation. And by the way, we can also federate to other OpenIO implementations. We don't need to use our Tensor Lakehouse implementation. And the idea is that then aggregations and filterings are computed close to the data. And so we minimize data transfer across data centers that way. In addition, we have here another row where we support directly grabbing data from the Tensor Lakehouse and streaming it to PyTorch. And that way we do not really need to download the data and just point it to our Tensor Lakehouse endpoint. Another interesting property here is the hierarchical statistical index, which it's HSI, we call it HSI. The idea is, I said already, the whole Tensor Lakehouse has the idea that you have a large, lazy hypercube, and then the indices are computed on subcubes at different resolution levels. And in those subcubes, we compute aggregations. And there are then two things which can happen. Either if you query, you can directly answer the question using the index only. You can completely skip this chain here. For example, if you want to aggregate over the time domain, sorry, the time dimension, most probably all what you need, all the aggregations are already present in the different HSIs. Therefore, you don't access the raw data. Or, for example, if you need to do intelligent skipping, like not reading data which is on top of oceans, for example, only on top of land areas, all this information is also found in the index. And there is a famous quote from Meta: you can't beat not reading data. So intelligent data skipping and read skipping is always important. Just to give you an idea how these HSIs are looking like. So on the left hand side, we have a 8 by 8 data set. So it's 64 data points. And then we group those into 4 by 4, so 4 times 16 data points. And on those 16 data points, we compute aggregation. So that's an example of the second smallest resolution level where we compute the HSI. And then you see on the right hand side some aggregations on top of that: 1, 1, 1, 2, 2, 1, and 2, 2 cells. And you see here there are some standard statistics, but also you can define your own statistics and add those to the HSI. Here's also the famous quote from Meta: no, you can't beat not reading data. No, I found this comment in the Velox source code, which was developed by Meta. Okay, so this is giving you an idea on the ingest and discovery capabilities of Tensor Lakehouse, and also on the parallel computing of the ingest using claimed. You can just run pip install claimed if you wanna have a look how this works. And then let's cover two downstream applications. One is TerraTorch. TerraTorch is based on TorchGeo, Torch Lightning, and PyTorch. And what we mainly do is we add additional data modules and modules. And all what we, for example, release on Hugging Face, we release quite a lot of foundation models and downstream models on Hugging Face. If you search for IBM Granite and IBM NASA Geospatial, you will see all the models we released. So we have foundation models, but we have also a lot of fine-tuned downstream application models. So you can have a look, and they are all predefined in TerraTorch, including third-party models like from Clay and from TorchGeo and so on. So it's your one-stop shop for geospatial deep learning, if you will, no? And it's also simple. It's pip install TerraTorch. There are some examples, and then it's TerraTorch fit for fine-tuning or TerraTorch predict for inference, and then you just pass a config file and potentially path to some files if that's not in the config file. Good. Okay, so now let's have a very, very brief look at the TerraTorch deck. So while this loads, I'll double check on the stream health. Okay, so there are no questions so far. Just if you have questions, put them in the chat. I will answer those. So that's TerraTorch. You might ask yourself why we are creating another framework if there's TorchGeo, but it's mainly because we want to support it in a way that you have a single config file expressing your whole inference or fine-tuning process. In addition, and by the way, also the model and the model architecture is defined in the YAML file. So we have building blocks like the backbone, which is, for example, the foundation model, and then you can add decoders and classification heads, regression heads, or segmentation heads, and so on and so on. And they are also coming from third-party libraries. For example, you can use a Clay Foundation model and some IBM classification head or so. So that's all something you can define. And then we have a hyperparameter optimization framework on top of it. And the cool thing is you can also optimize over the neural network model architectures. So that's a pretty cool feature. So let's double check if there's something important to show here. Okay, yeah, as you can see here, that's basically the component layout. Now you have here a data module wrapper where we can have stock data modules, or we wrap third-party data sets into that one. So you have a set of data modules which are already ready for you to use, and they can just be defined in the config YAML of TerraTorch and then just used. And the same holds here for the data geospatial data modules. And then we have the model. So we have a model factory and a model wrapper, which gives us a Torch Lightning module at the end and some predefined tasks. And that is all something you can compose your whole inference and fine-tuning pipeline using a single config file. And we have some examples in the TerraTorch repository. Okay, let's double check if there are any questions. No questions. Okay. Then the last thing I want to show you is another downstream application what we have built on top of TensorLakeHouse, and that exemplifies really the nature of TensorLakeHouse, the lazy layers, and basically the lazy hypercube. So the idea is, let me just open this application. And you can think of it like Google Maps for geospatial analytics. So it nicely fills the gap between, let's say, a Google Maps and QGIS or ArcGIS applications, for example. So this is planet Earth, no? So let's actually zoom into one example. So what we always see here is, let me deactivate that. We see a base layer, which is basically a satellite view of the planet, and that is just some data. We don't know exactly what date it's coming from. At least it's made cloud free, no? Mainly cloud free. So let's have a look at one raw layer. So this is now, let's zoom in a bit. This is HLS layer. So HLS stands for Harmonized Landsat Sentinel. So this is a NASA data set where they harmonized Landsat and Sentinel-2 data. And this is now image taken from one of those satellites in 2017. We have the same image for 2023. So it looks a bit different, but it's hard, obviously, to see the difference. So what we can do is we can apply a model. So we have a forest cover model. So let's apply this on the 2017 data. And you see here, this is the nature of layers. Now we have the base image, then we have one layer. This is a raw layer. And then on top of the raw layer, or with the raw layer, TensorLakeHouse triggers the creation and the caching of a derived layer, which is the forest cover, by applying a model, for example. And the same can also happen for the 2023 data. And now, since we have now created two derived layers from two raw layers, we can use the two derived layers and compute a change map. And that's becoming a fifth layer. And here you see then the difference in forestation. The green ones is a plus and the red ones is a minus. So overall, more trees are growing. in six years in Kenya. That's good news, no? And this is an example for Earth observation data. And let's go to an example of climate data. So let's load the Cortex data set. So this is here precipitation from the Cortex data set. And then what I can do is I can apply the foundation model which IBM and NASA created together. And that is the foundation model was used for a downscaling task. So the downstream task was a downscaling task. So downscaling is something like increase of resolution. So you see here, that's the increase of resolution, and we can also show it in that way. No, on the left hand side you have the raw data, and on the right hand side you have the output of the model, and that's just additional layers which are lazily offered by TensorLakeHouse. And whenever they are needed, they are computed. We call this lazy layers or lazy evaluation, and then cached. So if you access, for example, here this area, then the raw data is used to, and the model is applied. So this is inference, and then the data is shown. And if the raw data is not available, also the onboarding pipeline or process is triggered. So that way you can basically start with a completely empty Tensor Lake house, and whenever the downstream layers are accessed, the computation happens on the fly. And obviously you can also trigger pre-computation if you don't want to wait and some client or some researcher is needing the data by tomorrow, you can trigger a pipeline run, and this is then all pre-processed. Okay, so there are no questions. If you have any questions, comments, additions, complaints, please put them into the comments section. Otherwise, let's double check. I have one last thing I can show you is the architecture, because I said we use a lot of open source components, but not exclusively. And also we created a lot of open source components to the whole thing. So let's just have a look. Oh, this is loading. Let's wait a bit. Okay, so you see here at the storage side, all the different storage technologies are supported. On the left-hand side, we have the cluster storage like Ceph and Lustre and GPFS and HDFS and so on. And on the right-hand side, we have the cloud storage technologies. Then on the data side, we support key value stores. At the moment, it's HBase, but it's easy to add support for other key value stores. And then SAR and COG files, and also now we have support for NetCDF. We have indices. Those are at the moment stored in GeoParquet. We have some accelerators like PostGIS, where you are just faster. If you can think of it like a data mart, no, where you pull a subsection or a fraction of your data to have fast interactive access. On the compute side, it's X-Ray and Dask, GeoPandas and Arrow. One thing I didn't mention that's important. We use Stack. Maybe let's also go back to the poster, which is, you see here, we use PGStack. PGStack is an implementation of the Stack standard, which is quite nice. It is very fast. It uses PostGIS plus some custom UDFs implemented in Rust. Therefore, it's really fast. And the cool thing is, if you now have Stack for the geospatial case and Cloud Object Store, and then formats like SAR or Cloud Optimized GeoTIFF, you get this whole lazy implementation for free, because first of all, you start with a geospatial temporal query. That geospatial temporal query you issue against Stack. And what you get back is a number of Stack items, and all those Stack items have links to assets. And then those assets are either COG files or SAR files. And then in the metadata of those, you will find the offsets of the data contained. That means with a Stack query and with reading the metadata of the assets the Stack query returns, you already have created a lazy X-array. We are using the library Stack for that. And then that lazy X-array resembles the result of your query, but no data processing has happened and no discretes have been happening apart from the discretes involved in the stack query on PostGIS and reads for the metadata of the assets. So that's a very, very small fraction of reads which are happening to, for example, create a lazy X-array of a couple of terabytes of data. And then in the moment you are accessing a chunk in the X-array, then we already know in which file, on which URL, and on which offset we need to read, and we can read offsets from resources on Cloud Object Store via HTTP range reads, and we can obviously also read offsets of data files stored on a normal file system. That's business as usual, no? And that way we ensure that only chunks which are really accessed are read. And if you go through OpenIO API and you read a chunk which is not yet present, neither in stack nor on the data storage, then we can configure OpenIO in a way that it triggers the data onboarding pipeline. And if the chunk is on a collection, we call the layer collection in stack, no? If that is a raw layer, then the onboarding pipeline runs, which grabs that chunk from the third-party storage, for example, Copernicus or Sentinel Hub, or wherever you have your source data. And if this is a derived layer, we will compute this derived layer also by triggering that pipeline. And if it's a layer based on a model, we basically also trigger a pipeline, and that pipeline will, under the hood in the container, execute the TerraTorch code. And this TerraTorch code will use the model, read the raw data or the derived preprocessed data, and create a new layer. And then this chunk is present at the end when the whole process ran. So there's no need in like pre-processing the whole inference for the planet. You can just offer it as a service. You can tell the researcher you have now this model data applied to the whole planet, but only if the researcher accesses certain regions, then the process can be triggered. It's a bit slower, but that way you save a lot on storage and also on pre-processing cost. Okay. So there are no questions, then I suggest we will conclude. You now have also the link to my YouTube channel, and feel free to ask questions in the comment sections of the videos. I usually get back to you within one day or so. Thanks for joining and enjoy the conference. Thank you. Bye.